So, good afternoon, everybody. Thank you for attending this afternoon talk. My name is Nick Webb, and I'm a lecturer at the Liverpool School of Architecture. And my research investigates the use of digital tools to investigate historic works of architecture. I'm joined by Dr. Alex Buchanan, who's a senior lecturer in the Department of History at the University of Liverpool also. Alex's research is at the intersection of architectural history and archives, and she's previously investigated medieval vault design. So today we want to discuss our findings in relation to vaulting, obviously. Vaults are arch ceiling constructions, usually made out of stone, sometimes made out of wood though. And we'll talk particularly about our findings at Chester Cathedral. This is part of a lecture and workshop series. So for anybody who attended last week at Nantwich, we'll run it in a similar way. We'll talk about wider project aims, and then we'll go on to site-specific ideas. So here's a map of our different sites. We began collaborating, Alex and I, in 2014 after successful academic matchmaking by a colleague. And we were joined at this point by J.R. Peterson, who's a technician in the School of Histories, Languages and Cultures. And J.R. brings expertise in terms of specific digital tools. So early on, we received funding from the Paul Mellon Centre for Studies in British Art. And this allowed us to produce a digital survey of the medieval vault at Wells Cathedral. So we had to travel down to Wells to survey the vaults there to then work out how they were designed and constructed. But because Wells was so far away, as part of this funding, we had pilot studies at Nantwich St Mary's Church as well as Chester Cathedral. The reason we chose these is obviously that they're quite close to Liverpool, where Alex and I are based. So Chester began as more of a pilot study, but then as we started to investigate the vaulting at Chester, it evolved into something much bigger, and it's become a key part of our upcoming book. So in terms of when we went to Chester, that happened on Tuesday, the 14th of April, 2015, and it was the first place that we visited, so prior to Wells. And then we returned later in 2019 for a full colour scan, and we covered more areas as well. Our project expanded in 2018 when we received nearly £250,000 from the Arts and Humanities Research Council. That enabled us to add 2 more people to the project team, Dr. Sarah Hilson and Dr. Sarah Duffy. And that funding also facilitated this series of talks and workshops. Okay, so I'll move on now to why we're studying medieval vaults. So in 1841, Professor Robert Willis gave a lecture to the newly established Institute of British Architects. And in this lecture, he outlined his theories on how vaults were designed and constructed. So Willis was an engineer and academic at Cambridge. And he based his findings mainly on accessible vaults, such as cloisters, which are relatively low, and destroyed vaults, such as parts of Canterbury Cathedral. So we can see the left image at the bottom, which I've just highlighted. This shows the elevation of an east cloister bay at Norwich. And this was accessible to Willis because it's only 4 meters above the ground. You can see here I've ringed the people for scale, just so you can see the sizes of some of these spaces. Many vaults are much higher than those in the cloister at Norwich. For example, in the Lady Chapel at Chester, they're about 10 meters above the ground. Bigger still at Exeter, these are about 20 meters above the ground. And the biggest that we've found is the lantern at Ely, which is a whopping 44 meters above the ground. Many vaults were therefore inaccessible to Willis, and he used this talk he gave in 1841 as a call for more data. So if architects were to erect scaffolding to survey these structures, he was asking them for the information. So could you tell me the data about the vaults? He had little success though, with only Charles Barry giving him some of his data. We also need to question the accuracy of previous scholarship, which is based on analog tools and techniques. We see this, we have digital data, for example, again, of Norwich Cloister, and we can compare it with the data that Willis provided, and then we start to see inaccuracies with those analog methods. So in short, 180 years after Robert Willis gave his speech to the RIBA, we still don't fully understand how medieval vaults were designed. But now we have highly accurate digital methods of surveying vaults, and we have digital modeling techniques to analyze them. We can hopefully find out a lot more than he did. And I'll now hand over to Alex, who can give us a bit more background.
Thanks, Nick. So Chester, just to give you a little bit more of a background about the cathedral here. I'm sure some of you are very familiar with the cathedral, but we've got some other people from abroad who may not be as familiar with it. It starts off as an Anglo-Saxon church, which was refounded around the 1090s by Hugh I, Earl of Chester, as a Benedictine abbey, and rebuilt in the usual east to west sequence, with the west front apparently complete by around the 1160s. A few parts of this Norman building survive: the lower levels of the north transept and the northwest tower, and the west range of the cloister, which includes a groin-vaulted undercroft and a rib-vaulted abbot's passage. From the mid-13th century, the monastic buildings in the east range of the cloister were rebuilt, including a new chapter house, which had lancet windows and tiercern vaults. Work then started on an extensive reconstruction of the church's east end, starting with the Lady Chapel, with windows and vaults very similar to those in the chapter house, but bar tracery in the piscina, the holy water vessel washing space, providing a dating after 1250. We don't get tracery before that date in this country. The choir followed from around 1270, but construction was visibly prolonged. If you look at the cathedral, you can see how many changes are introduced and disrupted. And it's only described as being complete in 1332. Major 19th century restorations include the current wooden vault. In 1332, funding was obtained to rebuild the nave and the bell tower, but work didn't proceed beyond the east bays of the south aisle. In the mid-14th century, the resident saint, St. Werburgh, got a new shrine, and the south transept was enlarged. Work resumed in around 1385 when the crossing was remodelled, along with the north transept clerestory. And the nave was finally finished by Abbot Simon Ripley, whose dates are 1485 to 92. The last building campaigns consisted of the west front, the southwest tower, the north transept roof, and a revaulted cloister. The abbey was dissolved in 1537, and its church became one of Henry VIII's new cathedrals. Looking at this history, you can see there's a lot of complications, and we wanted to know what our data could add to understanding of the church. We had a number of research questions. The chapter house, the Lady Chapel, and the Slipe all have vaults with similar plans. So we wanted to know whether they shared geometries in 2 or 3 dimensions. Then we wanted to know how the design of these vaults related to other 13th and 14th century vault designs. But first of all, we needed to decide how we would capture the data we needed to answer these questions. And I'll hand back to Nick for this part.
So we investigated 3 different methods of digitally surveying the vaults, and Chester really was a place for experimentation, being the first place that we visited. So the first of the 3 that we looked at was total station. The way that total station works is you look through a viewfinder, and guided by a laser, you pick a point in space that you want to capture, then you press the side of the device, and then you have an XYZ coordinate in space. And you repeat this process. So for us, for example, tracing along rib intradus lines, we just follow along with a laser and pick all those points out. And we end up with something like you see in the center here. So a dot-to-dot version of the chapter house at Chester. So the advantages of total station, well, it's precise and selected, i.e. you're only seeing the parts of these points that you decide to select. But this is also a disadvantage, because if you want to record other elements, for example, rib profiles or the webbing, you need to do a separate campaign of recording. Another disadvantage is the scanning times are long. A bay at Chester took us nearly 2 hours. Finally, the scans that we produce using total stations aren't in color, and they only show these individual points. So because of these limitations, we decided to abandon total station and look instead at full laser scanning. So here we can see this is an example of full laser scanning. The scanner sat on the tripod in the chapter house again. So the way the laser scanner works is that it records the distance between it and every solid surface that it hits. But instead of doing a single point, as in total station, it does this hundreds of thousands of times over automatically. So it also takes a series of photos at the end of the scan cycle, and therefore we can assign color to these individual points, these thousands of individual points. So what we get at the end is something called a point cloud. And the best way to think about it is a swarm of bees, but in the shape of a building's interior. So what are the advantages of laser scanning? Well, the data is precise and records all details of the vault and the wider interiors. So even though Alex and I have been studying medieval vaulting above, it's also recording the walls, the windows, the floors. So if other people wanted to use our data, then they could. Laser scanning is also relatively fast, so it takes us between 10 to 30 minutes per scan. So for lower spaces, we use a 10-minute scan, so places like the chapter house and the Lady Chapel. For higher areas, such as the nave, we would use a 30-minute scan. Disadvantage, we end up with extremely large files, so you need a pretty powerful computer to do anything with the data. Another disadvantage is that the software and hardware is pretty expensive, so you're looking at around £50,000 as an investment. You can export this data though as orthophotos, and this is where perspective is removed to create orthographic plans and sections. So you can see that in the central top image here at Chester. Also, we can use laser scanning to create mesh models, and this is where the point cloud, so those individual, like a swarm of bees, they're converted into surface models. And you can see an example of a detail here in the bottom center. So if we just flick back to total station, you see the difference. We get this basic dot-to-dot plan and basic dot-to-dot 3D view in the center. And we get this very beautiful detailed 3D model using laser scanning. But there is a third method that we investigated, which is called photogrammetry. The way that photogrammetry works is you take hundreds of photos using a digital camera from as many different angles as possible to ensure that all different data and all details are captured. So you can see this is JR, our technician. He's taking photographs for photogrammetry in the choir aisle at Wells. And if you look carefully at the bottom, he's being watched over by the cathedral cat. So once you have all the all the photographs taken inside of the cathedral, you put it into a piece of software called Agisoft Metashape. And this can work out the perspective of where the images were taken from, and it figures out their position in three-dimensional space. And what it results in is, again, a point cloud model. And this can also, like laser scanning, be exported as orthographic representations, as well as 3D point clouds and 3D mesh models. So what are the advantages of photogrammetry? Well, it's inexpensive because you can do it with your own digital camera, or it could even be done using a smartphone in certain circumstances. And the software is only about £500. Also, you get some very high quality images out of it, and we'll talk more about that over the next few slides. And likewise, as a disadvantage, sometimes we found that the quality of the 3D data isn't as good as laser scanning. So we'll touch on that now. So here you can see this is the Lady Chapel at Exeter Cathedral, and this is an orthophoto. So this is one of the outputs of the scan data from that site. And looking at it and testing it, we were very happy with the geometry shown here, but the image itself is a little bit grainy. Here you can see this is the photogrammetry version of it, and the quality of the image is beautiful. It's much better if we flick back to the laser scan version. If we compare again, so photogrammetry, much better quality image, and the geometry looked good as well. But then we start to look at the details. So firstly, comparing point clouds of a column cut taken quite low down, about 1 meter above floor level. So if we look at that column cut using laser scan data on the left, we can see that we've recorded pretty good data to work with. And then if we look on the right, again, it's looking pretty good. So we're happy that at a low level, when you're quite close to a target, we could use laser scanning or photogrammetry to create 3D models for analysis. However, when we start to look at our areas of interest, which are predominantly the vaults, which are high above us, we start to see some issues with photogrammetry. So if we just look at the top left two images, we can see with the laser scan data, looking at the ribs high above us, if we take a cut through them, we still get a pretty good record of that rib profile. Whereas the quality really starts to deteriorate when we compare it with photogrammetry. Therefore, moving forwards, we chose laser scanning as our primary method to survey all of our sites. So here you can see this is a video of laser scanning taking place this time at Lincoln Cathedral. So just to demonstrate, if you look very closely at the top of the tripod, the scanner is spinning very, very slowly, and that's because it's shooting the laser out hundreds of thousands of times and recording those XYZ coordinates. And basically, what we have to do is just stand and make sure that people don't trip over the tripod whilst we're working on site. So once we have those laser scans, we have to record more than one. I should have mentioned that previously. So it works on line of sight. All of these methods, total station, photogrammetry, laser scanning, they all work on line of sight. So if the scanner cannot see the target, it will not record it. So what we need to do is create a series of scans that overlap, and we tend to take one scan per bay for most sites. So you can see here demonstrated using a point cloud model and different colors. For example, if we take the pink bay on the far left, we can see there's traces of pink in the second bay along. And this is because there's therefore an overlap with the red bay. So we're ensuring that good coverage. We have to register the scans, and what this means is that we need to align them. So when they come into the software, they could be anywhere in space. And the way that the software does that is it either looks for targets which we put up in church and cathedral interiors. So these are either checkerboards or they look like giant ping pong balls. And the software is able to recognize these and then triangulate in three-dimensional space how the different scans align. And more recently, with updates in the software, it can actually look at the different scans and recognize geometry amongst those different scans and align automatically. So the software is getting better all the time. So here's a plan of Chester. This was from our revisit in 2019. And just to show the little red dots of where we took scans. So we took about 30 on our revisit, and you can see we're very much focusing on the areas around the chapter house and the areas around the Lady Chapel. And Alex will touch on this later, but you'll notice that in the chapter house, we had to take 2 scans per bay rather than 1. So here are some of the outputs. This is a couple of ortho photos. Ortho photos is where all of the perspective is removed from the image. So it's the equivalent of an architectural plan and section. So we can start to interrogate this and work out what's going on with the geometry. So if we look, for example, at the plan view of the Lady Chapel of Chester at the bottom, we get these snaking ribs. So they're not going in a straight line, which was quite problematic for us. And you can see the left-hand bay here, how much the walls are distorted and moving inwards. So we have ortho photos that allow us to start looking at what's going on. And we have the 3D models. So this is one of the mesh models. And we can start to then rotate and navigate around that to see what's going on. And we'll just zoom in here so that you get a sense of how a mesh model works. So I'm just changing the view just to show all the mesh. So it's all those points of the point cloud which have been joined together to form triangles, and that gives us surfaces. Okay, so now we've got all of the data that we need to start with our tracing process. So what we're primarily looking at is the intrados line of each vault rib. The intrados line is the outermost edge of the stonework. Now, this is a really important point because you would have needed centering made out of timber. So you put that centering or formwork up when you're constructing the vault. And then over the top of that timber centering, you can put in the stonework. And then once it's all in place, you knock out the centering and hope that the stone above stays in place. So this would have been this critical junction where the timber and the stonework meet. And in the stonework, it's what we call the intradus line, it's that outermost edge of the rib. So for us, it's really important that we trace along that to try and understand the geometry. So here you can see this is an example of one of the choir aisles at Wells, and you can see where we've traced over all of those intradus lines on the 3D model in the center. And from that, again, we can start to export some 2D views. But starting to get into the key geometry that we need to look at, we take the traced lines, which are not true geometry, because as I mentioned before, they tend to snake a little bit. So the first thing we do is we run a best fit arc through that, and I'll explain further in the next video. But the key geometry that we're looking at once we do have a best fit arc is firstly the impost line, and this is the point on which the springing point of a rib appears to rest, and it's usually the abacus of a capital in medieval vaults. The next point is the springing point, and this is the lowest level of a rib, and it's usually covered by a boss. This is the lowest level of the rib, and it's where it departs from the underlying supports, and it's almost always a fixed point. The next point is the apex, which is notional, and that's because there tends to be a boss stone that covers it. Next, we need to look at the radius of each rib, and in some cases there are multiple radii for a single rib. And finally, we look at the center point of that arc in relation to the impost line. So we'll repeat this in a few slides' time because it's quite fundamental. I'll just finish this section though by showing a video of us tracing over one of the ribs at the North Choir Aisle at Ely. So this was a previous method we used and sometimes still have to use, where we're doing it by hand basically. So we're going into the mesh model and we're trying to pick out the points along the intradus line. So you can see that happening here. More recently, we use an automated process where we can tell the software to create a section along that intradus line. So here you can see now Blue Peter moment, all the ones we've done previously. Here's one I made earlier. But we can then start to pick out the individual ribs and we highlight them. So I'm just asking the software to switch on the underlying points. And then we use one of the tools in the software, which is a circle fit through point, and it automatically creates that best fit arc through the traced lines. So you can see that now shown as a purple circle. So the next thing we need to do is tidy it up. So the green line, which I'll now highlight in yellow, that's the impost line that we spoke about before. So we can trim that arc below the impost line, and then at the notional apex, we can start to trim that down too. So now we have that best fit arc and another Blue Peter moment. Here are all the other ones that we've prepared. We now have all the data that we need in order to extract into a data table. So the first thing we do is we ask the software, what is the radius of this rib? So it's about 3.5 meters. So we then copy and paste that into our Excel spreadsheet. And you can see in this spreadsheet that we're recording every single rib. And we're looking specifically at the radius, the apex height, and the center of the rib in terms of its relationship to the impost line. So here you can see recording the center of the arc in relationship to the impost line. This one's quite far below, quite a rare occurrence. So we put that into the table, and then finally we go back in and we find the missing notional apex. So hopefully that gives you an overview of the process that we go through. And now I'll hand back to Alex and she can tell us a little bit more about some of our analysis.
Thanks, Nick. But before we do that, let's look at the anatomy of a vault so we can all know what we're looking at. A Gothic vault has two main elements, the webs and the ribs. The webs, or the surfaces of the vault, were usually constructed from coursed masonry and plastered. In the Middle Ages, the webs would also have been decorated with frescoes, as we still find in Italy, and remains of these survive in some English vaults, such as those at Lincoln Cathedral, shown on the slide. The ribs are the mouldings, which usually mark the changes in plane of the webs, but could also decorate planar surfaces. The ribs were built first as a framework, and the webs were added afterwards, but both elements are equally important to the structure of the vault. Medieval vaults are not like modern steel frameworks infilled with non-load-bearing panels. The starting point of a rib, as Nick said, is called the springing, and the top is called its apex. At the apex, where a rib meets another rib, there is usually a sculpted boss. The bosses at Chester are very beautiful, and I'm showing one from the Lady Chapel showing the murder of Thomas Becket. Architectural historians have given ribs different names based on their location. The wall ribs mark the junction with the wall, and transverse ribs span between the side walls, marking the division between bays. A bay is a compartment of vaulting. The chapter house and Lady Chapel at Chester both consist of 3 essentially similar bays. Diagonal ribs cross the bay diagonally, and ridge ribs run along the crown of the vault, either east-west, the longitudinal ridge rib, or north-south, the transverse ridge rib. Additional ribs, which spring from the corners of the bay and rise towards the ridges, are called tiercerons, and those which don't start at the corner of the bay but start from another rib are called liurns. The Chester vaults we'll be examining today are tierceron vaults, whereas the 19th century vault of the nave is a liurn vault. We believe from our research overall that medieval architects started to design a vault by creating a plan of the ribs in 2 dimensions. This was laid out full scale on a flat plaster surface called a tracing floor. Very few of these tracing floors survive, although they're recorded in medieval building accounts, and we've been lucky enough to be allowed to scan the tracing floor at Wells Cathedral. From our data, we can create absolutely accurate 2-dimensional representations of the vault, from which we can start to hypothesize the process used to draw out the plan on the tracing floor. We know that the drawing tools available to medieval designers were limited. The main tool was a set of dividers or compasses from which they could create curves. They also had squares for creating angles and straight edges for drawing straight lines. Therefore, any design process we suggest has to be possible using only these basic technologies. In our workshop in 3 weeks' time, we'll show you in more detail how to use these basic tools to lay out a medieval vault. So what we're sharing today will just be a quick taster. As a reminder, the chapter house at Chester was rebuilt in around 1240 to 1250. It was part of the monastic buildings used for daily meetings of the monks, at which a chapter of the Rule of St. Benedict was read, hence the name chapter house. Here's a plan of the building as an ortho photo, so you can see the 3 bays and the plan with diagonal ribs, ridge ribs, and tiercerons. And here's the overlay with our traced lines. As I think you can see from our wireframe plan, the construction of Chester was fairly rough, although we don't think the inconsistencies we found are the result of subsidence, rather that the building wasn't erected to exact standards of geometrical accuracy in the first place. When planning a vault, the first stage was to lay out the plan of a single bay. This had already been erected when the vault was being built. At Chester, the central bay of the chapter house seems to have been laid out, as we'll talk through now. First stage, laying out the bay. Then the diagonals were added. The next stage was to divide the bay into quarters, giving the location of the ridge ribs. Creating chevrons in either direction creates what's been called the star cut, which our research has identified as a key design tool for medieval architects. We found the star cut in use at other sites. Its benefit was that it enabled a design to be transferred between bays using proportions rather than measurements. This was vital because, as we've already explained in relation to Chester, medieval churches were rarely constructed to the same accuracy as our scans, so any design had to be sufficiently flexible to be applied to bays of slightly different sizes. In the absence of accurate numerical measuring devices, using proportions would have been much simpler. The star cut could be used to divide a four-sided bay into any fractional proportion, up to 100ths. And so far we found thirds at Lincoln Cathedral, sixths at Wells Cathedral, ninths at Exeter Cathedral, as well as fifths, again at Lincoln, sevenths at Wells, and 13ths at Ely. Intersections of lines drawn in this way establish the position of all the bosses and the location of all the ribs. We then overlay our hypothesis over our original trace data to check their conformity. We're pretty confident that this represents a good match. However, if we overlay the same design on the trace design of the end bays of the chapter house, there's a clear discrepancy. We carried out the same process for the Lady Chapel, whose design we'll be exploring in our workshop in 3 weeks' time. We then looked again at the end bays of the chapter house. Again, the first stage was to lay out the plan of the bay. Then we add the diagonal ribs. Then we divide the bay into quarters to locate the ridge ribs. And finally, we needed to locate the intersection of the tiercerons with the ridge rib. We found that this could have been done in one of two ways, using circles with the diameter of either the length or the width of the bay. Using this circle to construct chevrons locates the apex of the tiercerons. The version on the left of the slide is a basic form of what we've called the inner circle star cut. The use of the star cut and its variants places the design process used at Chester within the mainstream of medieval geometrical design practices. We found the inner circle star cut in use at Wells and Ely, for example. However, the use of circle star cuts also reveals greater creativity in the Chester designs than had previously been identified. We found fewer examples of circles whose diameter is the width of the bay, but a variant of what we've identified as the possible method at Chester is used in the end chapel of the north transept at St Mary's Church in Nantwich. So here are our hypotheses overlaid over the tracings. As you can see, either of them is equally plausible in terms of the geometry, although we rather prefer the smaller circle method as it requires fewer steps. Again, overlaying this over the central bay reveals the discordance, which persuades us that a different method was used in this bay. So here is our final hypothesis. Once the two-dimensional design had been established, the designer had to work out how to make it three-dimensional. And I'll hand over to Nick to explain further.
When interrogating the design processes involved, we work from the basic principle that the 3D form of the vaults at this period is dependent on 5 different factors. The two-dimensional plan of the ribs, the height at which these ribs spring, known as the impost, as previously discussed, the height of the apexes of the ribs, the radius of the ribs, and the position of the center of the arc of the rib in relation to the impost level. Each of these factors could be used as a starting point, which limits the options available for the others. Once you have 4 out of the 5 and these are fixed, the 5th one automatically follows. And some of these elements could be fixed by the pre-existing architecture. So looking at the chapter house specifically, it seems likely that the height of the apex of the diagonal, transverse, and tierceron ribs was fixed, as these are the same height throughout. This could be based on a 2-to-1 ratio, i.e. 2 stacked squares, but we're not 100% certain about this. However, this isn't the case for the transverse ribs to the east and west, which have a higher apex. In terms of fixed elements then, all the ribs appear to have their arc centers on the impost line also. For all of the ribs other than the wall ribs, therefore, the known elements are as follows. We have the length of the rib in 2D, so we can see that the highlighted black line. The location of the plan and the springing, the location on the plan of the springing and the apex. So we have a blue circle in plan showing the springing point and a black cross showing the apex. Now if we switch to an elevational view, We also know that the height of the apex and the springing, so we know that there here is a blue cross for the springing and the apex is here as a green cross. And we also know that the impost line is in place and that the center of the arc was on this green line somewhere. So in this scenario, therefore, the radius is the unknown element, and we'll show it in red as we move through. So working from the known elements, we can find the missing radius by what we've termed the chord method. So first, draw a line between the springing point and the apex. Then draw a line at a right angle to the first line halfway along its length. The point at which this line crosses the impost line is the position of the center. And the distance between this point and the springing and the apex is the radius. So we can see now we've found the missing arc shown in red. And this is the process that's used for many of the ribs at Chester. And then we continue this process and hypothesize how it worked for every single rib. And I'll hand back to Alex now for some further remarks.
Thanks, Nick. So as we've already mentioned, the vaults at Chester show remarkable similarity in basic layout. Specifically, the omission of the last span of the ridge rib between the final boss and the end walls. We find this in the chapter house in around 1240 to 50, the Lady Chapel in around the 1270s or 80s, and the Slipe in the 14th century. But there were nevertheless significant differences in their two-dimensional geometry and also their three-dimensional forms, which are revealing of wider trends in tiercer and vault design. So if we look at the chapter house and the Lady Chapel, they both have ridge ribs which arc between the bosses. You see that? And we find this at numerous other early tiercer and vaults. For example, at Lincoln Cathedral here, again, you can see these curving ridge ribs. And if you compare this with the angel choir at Lincoln, we've got flat ridge ribs there. So I think you can see the very clear difference between the earlier St. Hugh's choir and the later angel choir. If we move back to Chester from Lincoln, you can see that in the Slipe, which is 14th century, we have this straight ridge line, which we don't find in the earlier vaults. We go on to the next slide. We also find that the ridges in the chapter house rise up. So we had the ridge ribs only go as far as the boss, and then we have an uncovered ridge line going to the windows. And in the Lady Chapel, it goes upwards towards the window. If you remember that Nick said that we had to take 2 scans in the chapter house per bay, and this is why, because the vault kind of, if you're standing in the middle, you don't see the whole of the vault. So we had to take 2 scans because these vaults rose up towards the windows. If we go to the Lady Chapel, on the other hand, the ridges sink towards the windows. The highest point is in the centre of the vault. Again, we find both of these features in other vaults. So this curving down, for example, we find in the presbytery at Ely Cathedral. So it's quite interesting to see the differences in three-dimensionality between these 3 vaults, which look in plan to be very similar, but once we go into 3 dimensions, we see that they're quite different. Another of our findings was in relationship to the bosses. Now, I mentioned that in all of these vaults, we don't have a rib between the final tiercer and boss and the wall rib. But at Chester, it looks as though these were originally planned, because if we look more closely at the bosses, we see that there's a broken off stub of a rib that would have gone to the wall rib. And if we look at the wall rib, again, we see a broken off stub, which would have been the other end of this rib. So we don't know why it wasn't filled in, or whether this is something that was taken out during restoration in the 19th century. This is one of the things that we want to do more research on at the next phase of our project. And there are some other things that we're looking forward to researching, again, maybe relating to the 19th century restoration. In the side aisles of the South Choir and the eastern chapels of the South Transept, there are remaining Springer blocks from medieval work, which were then completed or rebuilt in the 19th century during restoration. Nicholas Pevsner was the first to point out that the geometry of the 19th century vaults entirely ignores these medieval starting points. So we want to see whether with our techniques we can reconstruct them as the original designs were intended rather than as they now are. So that's one of the next stages of our project, was to look at how these vaults might have been intended to be built rather than how they actually survive. So we've still got a lot of questions in relationship to Chester. If you'd like to find out more about our project, please check our website, which has lots more about our various sites. It's about to be relaunched, so please keep checking back because there'll be more and more information available. You could also subscribe to our newsletter by scanning the QR code or by following the link that Nick is going to put into our chat room. You can also find this on our website. And our book, Digital Analysis of Vaults in English Medieval Architecture, is currently being indexed and should appear later in the year. So do look out for that. Chester features in it. So you can find out more about what we've done and how Chester relates to other vaults by checking in this book. It'd be wonderful if you could join us in 3 weeks' time for our workshop. If you sign up via Eventbrite within the next week, you will get a pack which contains compasses and some worksheets to be working through. It's possible to sign up after that, but you won't get the pack, I'm afraid. So do sign up for that. We would also request that you fill in our feedback form. We'd really appreciate finding out more about what you've got from this talk. This both helps us to improve our talks for future occasions and also to argue for more funding for this sort of work. You can either do this by following the link on chat. If, on the other hand, you have any problems, the link will be sent to you via email as part of the thank you for coming to the talk. And we can also send you a Word version. So if you have any problems using the online version, well, you can fill it in Word. It's only a very quick survey. It should only take 2 to 5 minutes. Thank you very much. Do you have any questions?